Hello, everyone. I'm Radu Kalinescu. I'm professor of computer science at the University of York, and I am the principal investigator on the research project that is organizing this seminar series on the resilience of autonomous systems. And I'm really delighted to introduce our speaker today, Lina Marsso. Lina is currently a postdoctoral researcher in the Department of Computer Science at the University of Toronto. She received her PhD from UNIA Grenoble, France, where she carried out work in the area of verification, model checking, and this is also what she is working on at the moment, but in combination with the safety and analysis of automotive systems. So I'm very much looking forward to this talk, and it is over to you, Lina. Thank you.
Thank you very much, Radu. Thank you very much for letting me do the talk today. My talk is entitled Verification Analysis of Automotive System Perception Components. So autonomous vehicles are complex and safety-critical, where an undesired behavior could lead to fatal accidents. For instance, we have the Uber SUV accident in 2018, where the perception component failed to detect the pedestrian, and this led to a crash. It's important to evaluate the safety of the autonomous vehicles and their components before deploying them. And it's not really possible to do it in the realistic environments because it's expensive and unfeasible to reproduce critical situations such as collisions, near miss, or to reproduce different visual changes such as some fog, some rain, etc. So a common practice to validate autonomous vehicles and their components is to use virtual validation. So the idea of virtual validation is to simulate the environment that includes the roads, the sidewalk, the building. It also includes different visual changes such as some rain, the traffic lights, the signs, and the actors with whom the autonomous vehicle is sharing the environment. So to do this, one must first specify the scenario, which is a precise definition of a given environment, and the trajectory of the different actors with whom the autonomous vehicle is sharing this environment. So their initial position, their speed, and their destination. The advantage of virtual validation is that we can focus on some specific safety-critical scenarios, and we could execute many virtual scenarios in parallel. So in this talk, I will focus on the perception component of the autonomous vehicle, on two types of perception components. So the ones that are simply probabilistic perception components, and the other ones that are using machine learning. For both components, there is a wide range of possible critical scenarios that could occur in real life, and according to who we would like this perception component to be reliable, and also different visual changes that could happen in the environment. It's very hard to validate perception components manually, so it's important to establish some automatic methods that are systematic and that enable us to verify whether a perception component is valuable to a given environment. So the first part of the talk will be an approach that enable us to verify a perception component that is probabilistic. And the second part of the approach of the talk, is a second approach that is the validation approach that is checking perception components that are also probabilistic, but that are using machine learning. So these two works are made in collaboration with different researchers from 4 areas, from software engineering, machine learning, robotics, and formal methods. Involved, these are my supervisors. So for the first part of the talk, perception components that are not using machine learning. So the context is virtual validation. existing approaches that are generating autonomous vehicle scenarios are often restricted to specific configuration. We can see often the highway overtaking configuration, but in the realistic environments, we have different types of configuration. We could have a crossroad, we could have a simple road, but in the city, not necessarily in the highway, etc. There's also many approaches that are based on parametric scenarios, which are restricting the behaviors of the actors, which is also not representative to the realistic environments. Therefore, we need an automatic approach that is generating different autonomous vehicle scenarios that could represent the realistic environments that are not restricted to specific configuration. And we also need an approach that connects these autonomous vehicle scenarios to the perception components to enable us to verify whether they are reliable or not. So we proposed an approach that, given a formal specification of an environment and a specific situation, generates some autonomous vehicle scenarios, executes a perception component on these autonomous vehicle scenarios, and check whether the outputs of this perception component are reliable or not. So the first step of the approach is to formalize the virtual environment that we would like to generate autonomous vehicle scenarios from. So first, we should formalize the geographical map that contains the road and the different actors. So we formalize it with the grid, where each shell could be either free or contains unmobile obstacles, or a mobile obstacles, or the autonomous vehicle by itself. The obstacles could be transparent or not, which means that if they are transparent, we could see behind them, and if they are not, we couldn't. A building is, for instance, an obstacle that is not transparent. So we consider this geographical map grid as a ground truth, where each position of the obstacles and the car should be updated in real time. Then we formalize the perception grid of the perception components, where each shell could either be free or it could contain an obstacle that is immobile or mobile. If the obstacle is not transparent, the cells behind the cell of that obstacles are considered unknown because we couldn't perceive what is behind. This perception grid is centered around the autonomous vehicle position. So we use CIDP, which is a verification toolbox. Specifically, we use the formal modeling language for the behavioral specification language and the property specification language. We also use their verification tool. So for the behavioral specification language, we use LNT, that I like to call a user-friendly formal language, because it combines 3 different paradigms: process calculi, which enable us to specify non-deterministic behaviors. It also contains functional language paradigms and imperative language, which is very close to common programming language. So we could see the if, while, for, case, etc. So using LNT, we made a formal model of an autonomous vehicle that has 1 perception component and a moving car component. We also formalize the environment that consists of an obstacle manager that is managing the position of the obstacles, and a map manager that is updating the position of the car and of the obstacles in the geographical map grid. Our formal model also has 2 other processes, scheduler and restraint, that are restraining the position of the obstacles around the car, because this will lead to relevant scenarios. It's not really interesting to have some obstacles very far from the car and not have a chance that the perception component could even perceive them. So after formalizing our formal model, we use the compiler to generate the input-output level transition system. So here it's an expert of the formal model. The idea is not to be able to see what is there, but just to have a global idea. In blue, we have the inputs, which are controllable, and in black, we have the outputs. So now that we have a formal model, we would like to be sure that the formal model corresponds to the environment that we wanted to specify. To do this, we will check whether some properties are satisfied by this formal model. So we would like to be sure that the formal model does not contain any deadlock. We would like also to be sure that inevitably the system should reach a state where the car arrived at destination, or there was a collision between the car and an obstacle, or all the obstacles have finished their list of actions. And finally, we would like to be sure that if there is a collision, it's not caused because of an obstacle, but it's caused because of the car. So we formalize this property using MCL, which is the model checking language of CRDB. So here we have, for instance, the third property that is formalized. So we want to be sure that we don't have sequences where the car is at one position and then the car doesn't move. And then we have the obstacle in another position and the car still doesn't move, is in the same position. And then we have the obstacle in a new position, which leads to a collision, which would mean that we don't want to have any collisions that happen because of the obstacle move or not because of the car move. So now that we have checked that our formal model corresponds to the environment that we wanted to specify, we would like to generate the sets of test scenario that contain a specific situation. To do this, we use conformance testing, which is checking the conformance between a formal model and a system under test. So specifically, from a formal model, we generate a test case that is controlling the inputs on the system under test and observing the output of this latter one. If the outputs are conform to the one that were specified in the formal model, we say that the execution of the test case is a pass, otherwise it's a fail. But in our situation, we are interested in a specific situation. So we specify a test purpose, so the specific situation that we would like to test. We generate a test case that enable us to test this situation in the formal model. And when we execute this test case, we have a third verdict, which is inconclusive, which means that the execution of the test case is conform to the formal model. It did not fail, but we were not able to see the functionality that we wanted to test. So for instance, if we would like to specify the situation where we have a collision, so we would like to generate a scenario where we would like to see the car in collision. So we specify the test purpose using the input-output level transition system. We use TestStore, which is an on-the-fly conformance test case generation tool. So that takes as input the formal model, the situation that we would like to test, and generate as the outputs the complex test graph that contains all the possible scenarios in the formal model where we could reach the situation that we would like to test. So here we have an excerpt of the complex test graph, where we have the input in blue and the output in red. So the input is what we would feed the system under test, and the output is what we will observe. In the test graph, we also have the verdicts, pass, fail, and inconclusive. And now that we have all the possible scenarios that lead us to this particular situation, we would like to extract from all the scenario each singular scenario to be able to transform them into autonomous vehicle scenarios. To do this, we use the test extraction tool that, given a complex test graph, will generate a set of test cases that is covering this complex test graph. Alternatively, we could also use directly the formal model and not a specific situation to test, but in our case, we're interested into a specific situation. We only want to have the scenario that leads to a collision. So we obtain the list of test suites, and now we would like to transform them into autonomous vehicle scenarios. So to do this, we transform them into behavioral tree. So first, we initialize the behavior tree with all the different actors that are in the scenario, their initial positions, and their sequence of move. So to do so, in our behavioral tree, we have the yellow nodes, which are executed in sequences. And under each yellow node, we have the purple nodes, which are executed in parallel. So we have, for instance, the first step, the car A and the car B that could be in this position. In the step 2, we want them to to see them in another position, etc. We also translate automatically failure and success condition of the behavioral tree. So in our test test purpose, the success condition was the collision. So the execution of the behavioral tree will succeed if we observe a collision. And the failure condition would be, for instance, a timer or the trajectory that was not following properly, etc. So now that we have our behavioral tree, we also need a perception component that we would like to check whether it's reliable given this autonomous vehicle scenario. So we chose to use CMC dots, which is a perception component that, given some sensor data from a LiDAR, for instance, computes an occupancy grid where each cell could either be empty or contain a static or dynamic obstacle or be unknown, which means that the perception component was not enabled to perceive. CMC.dot also compute 3 collision risk estimations, one at the current time, one at time plus 1 second, and one at time plus 2 seconds. So given this CMC.dot on our behavioral tree, we use Scala as autonomous vehicle simulator that we connect to CMC.dot using ROS, which is a communication framework, and we execute the behavioral tree on Scala. We obtain the output of the perception components that are that we call execution traces, where we log at each timestamp the collision risk estimated by the perception component and the ground truth telling us whether or not a collision occurred. So now that we obtained the perception component output, we would like to determine how reliable these outputs are. So we would like to verify whether the perception outputs are reliable or not. To do this, we follow an existing approach that was validating the collision risk estimation. But the current approach was not handling nonlinear obstacle behaviors, but in our case, our obstacles could slow down or they could speed up, for instance. And therefore, what we did, we first grouped all the execution traces into segments where the actor behaviors are stable. And then we verified 3 properties. We verified the estimation coherence, the prediction safety, and the appropriate progression. So we say that if high risk estimation probability occur, it means that there is no doubt that the collision occurred. And if a low one, there is no collision. But because there is some fluctuation, we consider the probability from 0 to 0.1 that there is no collision, the probability 0.9 to 1 that there is for sure a collision, and in between, we consider that is an unknown interpretation because there is like 50% of mistakes. So taking this, we will read the triple of risk estimation collisions as follows. If we have 0.051, it would mean that a collision is expected within 3 seconds. But if we have, for instance, the following triple, which is 1.050, it will mean that the collision will occur during the next second, but not during the next 3 seconds, which is not really possible because if the collision occurs, it will occur for more than 1 second. So the first thing that we would like to verify is that the coherence between each triple. To do this, we formalize the estimation coherence property, which is an equation, and that ensure that each risk collisions are coherent. So we have 10 coherent configuration out of the 27 possible. So we use XTL, which is the executable temporal logic model checker of CIDP, to check whether the invariance holds in the execution traces by simply formalizing the inequation. And then we check the 2 other properties. So the first one, prediction safety. So the prediction safety property detects bad predictions. So in our case, we consider that if the perception components say that there is a collision should occur. And if the perception component does not predict a collision should not occur. So to do this, we formalize it using an observer automaton, where in the first step, if the perception, if the prediction is correct, we move to the next step. Otherwise, we go to the failure state. The same one for the estimation at 2 seconds, and the same one, and the same case as the estimation at 3 seconds. And then we have the last property, which is prediction progression, that checks whether the risk estimation progress currently. For instance, if the first triple was there is no collision, the next one should be that maybe a collision occur, and then it will still be maybe, or there is a collision, etc. So after checking our 3 property, we log the violating events with the wrong prediction, and we use them to compute a quantitative grade on each execution trace for each property. So we conducted experiments on 6 different configuration, some of them with a crossroad, some of them with an obstacle that doesn't move, and we wanted to have a collision somewhere there is no collision and the car arrives at destinations, some on the highway, etc. So we transformed our test cases into behavior tree, and we executed the perception components on these autonomous vehicle scenarios, and we obtained the execution traces. For the 2 other properties, the progression and the currents, the results were simply correct. There was no interesting things. But for the prediction safety, we observed that if we sort the grades by scenarios, that the scenario where the obstacle doesn't move, the perception component is not as valuable. So because the perception component is very good at trying to predict a collision in advance, and in this case, it's something that it's a scenario that the perception component did not have to handle. It's still quite good if we see, because if we check the scale, it's from 0.80 to 1. But because it's a safety property, we should expect the perception components to be always correct, so never give unsafe predictions. So I forgot to give the legend, but each point is the grade, and when we have a wider range, it means that many grades are in the same position. So to summarize, in this first part of the talk, we propose an automatic approach that generates some autonomous vehicle scenarios from a high-level description of the situation. The guarantee is that all the possible scenarios are relevant given the specific situation that we wanted to test. And this approach is also directly applicable to other perception components that are also computing collision risk estimation. So it could also be the one that are using machine learning to compute the collision risk estimation. As a next step for this part of the talk, we would like to connect it to other autonomous vehicle components, specifically the control component, because we believe that we could extend the approach to perform online performance testing. It is something that we couldn't do in the perception component, but that would work very well with the control component.
Lina, since you are
yes.
halfway through the presentation, would you be happy to take a few questions? Because I'm seeing people are asking them in the chat. Would that be fine?
Of course, please. I don't see the chat, so if somebody
could... I will invite people to ask these questions. So, yeah, maybe Grisel, you are you had a question.
Can you hear me?
Yes, we can.
Yes.
Thank you for the talk. Middle. I was wondering, how did you get the data for the different scenarios?
So the
yes.
data. So like, okay. So I will describe more. I don't know if I understood the question. So here we have like the 6 different scenarios. In each scenario, we have a number of obstacles. So it was like 1 obstacle for 4 of them and 2 for 2 others. Here it's lines of code for the formal model. And here it's state transitions for the formal model, the number of states and the number of transitions. Then after this, we specify some test purpose. So we either wanted to have a collision or we wanted the car to arrive at destination. Then we compute the complex test graph that contains all the possible scenarios leading to this test purpose in the formal model. So we can see that it goes from so this is like the number of states and number of transitions. The most interesting is the number of test suites. Then from this complex test graph, we generated all the possible test cases in each complex test graph to be able to transform them into behavioral tree. And we can see that for the first models, we generated between 3, between 3 and 69. And for the other models, we have up to 500 test cases generated from the complex test graph that we transformed into a JSON file to be able to transform them into behavior tree. So this is mostly quantitative numbers of how many test scenarios. And then for each JSON file, that we automatically transformed it into behavioral tree. And each behavioral tree, we generated different versions with different speeds. So it's a linear speed. So for the first one, we did, like, for instance, 20 km/h. The next one, 25, 30. For the car obstacles, we had a bit more. And here, the trace and the lines are the size of the execution traces. Yeah, that is it. So I don't know if I answered the question.
Yeah, perfect. Thank you.
You're welcome.
Jinwei, if you can ask your question.
Yeah, sure. Thank you. So my question is, when you're formalizing your problem using occupancy grid, how did you determine the resolution of that? Because in my opinion, is if you have a huge resolution, which is 1 grid represents for a large area, you less likely to encounter problem.
Yeah, it's a very good question. So there's 2 grids, right? So it's not the map grid. We're speaking about the perception grid, right? So first of all, we have to formalize the map grid because these are all the possible scenarios that we could have. And then when we are specifying a specific situation that we would like to test, it will cut the possible movement of the obstacles on the car in this given grid. So our perception grid is very small. Our idea is to restrict the position of the dynamic obstacles around the car, to not have some obstacles in some other places, and it will just explode the size of the model while it will not be useful. We realize that most of the autonomous vehicle scenarios, they're very short. The idea is not to have something long. They often have like 1 or 2 obstacles, and they're often like doing very simple trajectory. So we decided to put a scale. So if we check the behavior tree, what we have here is time points, which means that our model is discrete, but the scenario is discontinuous. And what we are expecting is we are given a trajectory by expecting the actors to arrive in different places by giving them some time points that they should check in their trajectory. So we draw it. So the size of our grid should correspond to the discretization that we would like for this time span. So I would say that for a highway, for instance, we could put a bigger size size, because there will be like less movement on less possible trajectory. But if we formalize, if we take, for instance, the crossroad, which is in a city, there is different positions that the obstacle could do. So we need more time point to be sure that we have the trajectory that we would like to test.
Okay.
And and these trajectories are directly generated. We did not specify them. We only specify that we would like a collision, and then our generation approach will automatically generate the trajectory that will lead to a collision.
Okay. Thank you.
So
You're welcome.
maybe one last question before we move on with the presentation, Janina.
Okay, thank you very much, Rado. Nice presentation, Lina. Thank you for the work you did here. Sorry, my camera. Okay, finally. So actually, I was impressed by the end-to-end approach that you brought here in this work. So congratulations for aligning all these ideas and making it feasible. So out of many questions I would have, but mostly for curiosity. But I'd like to know, since you're talking about safety, usually when you go into the robotics domain, you usually define like a safe area that the robot avoid colliding with the obstacles in the environment. So of course, in your, let's say your Carla simulator, you define that. So I was wondering how you define the safety zone, and especially when talking about speed, how do you really balance out, since you were talking about real numbers, not only discrete numbers? So this would be my first question to you, how you kind of dealt with that. And the other one, I liked the approach that you used, the observers, for when you express some of the safety properties you wanted to analyze there. So I was wondering how you sure or how certain you are that this property really capture the environment issues that you have there, because you have so many variables, so many possible states that the system can fall into, and how do you really make sure that you're capturing those observers, those states properly in your observer automata?
Okay, yeah, it's a very good question. So what is interesting is that this work is a collaboration with the robotic team that are the ones that are developing the perception components. So in what they wanted initially when they come to talk with us is that they have this estimation of collision, and they wanted to be able to validate it, because now in the robotic areas, they are asking them a lot of certification. And the first step was, yes, to define what does it mean to be correct and what does it mean to not be correct. So in their situation, it was not yet given the environment, but given the component by itself. What does it mean to have good or bad risk estimation, so collision risk estimation? So this is something that was initially done by another student. So what he did in his project, he specified the three properties. So taking into account that the risk estimations are probabilistic, and that they have a link, since it's the risk of collision in 1 second, then 2, then 3. The properties that he came up with are the ones that are ensuring the coherence between the risk estimation, the ones that are telling that they are good or not, which in this case is quite simple, since the risk estimation is that there is a collision or there is no collision. So to be sure that when it's telling that there is a collision should happen, and when there is not, the collision should not happen. And the third one is the progression between them. And what we did in our work, we extended it to be able to handle non-linear obstacle behaviors, and we connected it to our generation approach. But initially, the three properties already existed. Is there some other properties that we could have verified? I would say yes, for sure. Do I have an idea? Not yet, but we did not do yet some properties that are connected to the environment. And I agree that I think that if we add some other properties, it should be some that are specific to a configuration, so not generic to the perception component. And that would be like in a given environment, taking into account that this will happen, we want to be sure that the perception component is correct in that term. But this is something that we did not explore yet, but it's a very good comment. And then, so I think it also answers the second question, which was about the observer automaton. So since it's the same property that we are checking, in our case, it's very simple, since we have this probability where we could either have no collision or there is a collision. And then we have this triple, and the number of configuration is finite. So then we can simply hardly define what does it mean to be coherent and what does it mean to not be coherent. And this is why we can do it in this way. So if we check some other properties, I guess it depends how we will formalize them and how we will check them. But this is definitely something that we are interested. This is why in the future work we are interested at trying another components, because the problem of perception component is that we cannot do much. Like currently, like this robotic team, when they are checking whether the perception grid is good or not, they do it with their eye. There is not a way to put a grade to a grid. So to be able to, so in this work we are only able to verify the risk collision estimation, but we cannot evaluate the occupancy grid, because so far the occupancy grids they are evaluated by checking them whether they are good or not, but they are working at establishing metrics to be able to verify that an occupancy grid is the one that we expect or not. And if this thing is not yet done, we cannot do more, I believe, but it should happen soon. While if it was like, for instance, the control component, it's a bit easier. There is some movement that the control component should do to avoid, and if there is a way to avoid a collision and the control component did not take it, it's something that we can specify and that we can check. I don't know if I answered properly.
Thank you very much, Lina. Very nice, very nice. Thank you so much.
You're welcome.
Thank you for already answering all these questions, Lina. So I propose that we move on to the second part of your talk, and we would be really grateful if you could leave some time for questions at the end as well.
Okay. Sure. Thank you very much. So the second part of the talk is an approach for validating perception components that are using computer vision. So here, in this context, we are interested at the perception component reliability, again, visual changes that could occur in the real world. So this is something that was quite explored in the community, but very few people focus on how much visual change we should check, what are the range of changes, and what should we expect from the perception components. Because the perception components are here to replace humans, what we argue in our work is that we believe that we should have a perception component reliable as long as humans would have been. So they could replace humans if they are at least as good as humans. Therefore, we propose an approach that is using human performance as a baseline to define the reliability of perception components against these visual changes that could occur in the real world. So we define it as the following. If the changes are not affecting humans, they should not affect the perception components either. So we specify two reliability requirement classes for the perception components with the parameter representing the human performance and the method to instantiate them and to check whether an MVC, a perception component, is reliable to these requirements. So for instance, if we take these four images, we can all agree that here we can still predict that there is a car. We are still also able to see that there is a car. We add a bit more frost. We can still see that is a car. We add a bit more frost. And here, I guess we can all agree that we cannot see anymore the car. So the idea would be to not expect the perception component to be reliable if humans cannot. But for all the range of changes that is not affecting humans, we expect perception components to be as reliable. So we need to estimate this range of changes that is not affecting humans. And we do this by conducting an experiment with human participants. But first, we need to establish a metric that is measuring how much changes is added to an image. So we define the visual change metric that is using image quality assessment metrics that is measuring how many change is added from an original image. Using this metric, we sample images within a wide range of image changes from the whole range of these metrics, so from 0 to 1. And we show these images to human participants for 200 milliseconds. Then we ask them what is the category of the object that is shown on the images. We collect the prediction and then we put a noise to refresh for the next image. So it's very important to time the experiments to be sure that we obtain a fair comparison between humans and machine. So after conducting this experiment, we obtain the range of changes that is not affecting humans. So we can formalize our requirements. So we have two requirement classes. The first one is correctness preservation requirement class that is requiring the perception component to preserve as many correct predictions as on the image that undertook changes in the range of changes that is not affecting human performance, as it was preserving the amount of correct images on the original images. So if my perception component had like 80% of accuracy on original images, on the transformed images within the range of changes that is not affecting humans, we would like the perception component to preserve the same amount of correct images. So to do this, to obtain this requirement, we need the controls because we need to know what are the correct predictions. So we have a second prediction preservation requirement class that is not requiring the controls, but is because it's expecting that the perception component preserves the same predictions on original images than on images transformed with the range of changes that is not affecting humans. So in this case, the controls is not required, and we are not comparing to the controls, but we are comparing the same output. So we expect to have the same output on original images and on transformed images within the human-interpreted range. So these two requirements are complementary because the first requirement requires the controls, which is quite expensive. The second one is directly applicable without having labeled images. But the problem of the second one, if we have a perception component that is very bad and always give the same wrong answers, it will satisfy this requirement, but which will not mean that the perception component is good. And at the same time, if we have a very good perception component that preserves correct answers, but that does not preserve the same one, it would mean that we don't have a coherent perception component, which is not ideal. So ideally, we would like the perception component to satisfy the two requirements. So to check the satisfaction of these requirements, we generate test images within the range of changes that is not affecting humans. We feed these images to the perception component, and we obtain a perception component output. And then, giving the perception component output, we first check the correctness preservation requirements by comparing the outputs to the ground truth. And we check then the prediction preservation requirements by comparing the output to the original images output. So we wanted to evaluate our approach. So our first question was whether the existing approaches already handle the range of changes that is not affecting humans. And in this case, it's not necessary to do all this tedious work to obtain the human-interpreted range of changes. What we did, we compared the range of changes, the human-interpreted range of changes with the range of changes of images from the Cypher 10C, which is image corruption dataset that also considered realistic image transformations. So here we have the number of images, and here we have the visual change metric. So we can see that the range of changes is never addressed by the ImageNet 10C image corruption datasets. And we can also see that the distribution of the images is not fair, and therefore the evaluation results might not be representative. For instance, for JPEG, we can see that most of the images are within a very small range of changes. And for contrast, for instance, we have like images with the same range of changes, with very few in the beginning. So we wanted to see if giving this unfair distribution of test images, we will discover more reliability gaps than the current reliability benchmark. So what we did, we compared the leaderboard of the ranking of the leaderboard of the benchmark with the leaderboard obtained by checking whether the perception components are satisfying our correctness preservation requirements and our prediction preservation requirements. And what we observed is that, for instance, for LLAT, that was first, is still first for the prediction preservation, but for correctness, it becomes one of the last ones, which means that it was probably bad and did not preserve the right ones. And if we remember, for the compression, the distribution was really imbalanced. And we also realized that for the second perception component, for the prediction preservation, it's one of the, it's actually the last one. So realize that it's very important to have a better distribution of test images, and that the range of changes that is not affecting humans is not yet tackled by the current state-of-the-art perception models. So in this part of the talk, we define reliability of perception components as if human can see, so should the perception components. We propose two reliability requirement classes and the framework for instantiating them and checking whether a perception component is reliable. As a next step, we would like to extend this reliability requirement to other type of perception components. Would like to develop a method to reduce the cost of the human performance and to extend the checking method with the reliability diagnosis. I would like also to connect the range of changes that is not affecting humans to the generation of the scenarios to be able to see how the perception component is reliable with scenarios that include this range of changes. So as the current progress and recently submitted work, we proposed an approach that is decomposing complex vision tasks into the analysis of complex vision tasks into the analysis on their subtasks. So for instance, if we have object detection that consists of localizing and classifying the localized object, we are proposing an approach that is analyzing the localization by itself and then the classification of the localized object, which enables to localize the failure. And it's also provide a bigger diagnosis and enable to reuse existing reliability analysis artifacts for the subtasks. So this work was made with my collaborators, and thank you very much. I would be open to any questions.
Thank you very much, Lina, for this really insightful presentation. If anyone has questions, we have about 10 minutes left for a discussion. Would you like to start, Grisel, maybe? This could be questions on either part of the talk.
Yes, it's a very interesting talk. And related to the first one, I got another question in my mind, and it is how do you differentiate between scenarios? What are the differences between them? Is it the movement of the robots? Is it the obstacle space around them?
Okay, so it's for the first approach, right?
Yes, like turning right, turning left, moving forward.
Yeah. It's a very good question. I'll try to, yeah, we'll put this. Okay. The first step of this approach is to formalize a formal model that is giving like a map. So which are the possible directions we could go? What are the mobile obstacles? So if there is some buildings in the map, maybe it's simpler if I show the grid. Yeah. So where do we have some buildings? And then we have the mobile actors, which is the autonomous vehicle, and the obstacles. So according to the scenario, if the user decides that the trajectory of the autonomous vehicle is fixed, one could fix it. Or
So
one could only give.
So the grid
Yeah.
is the same for all the scenarios?
So the position of the car and the position of the actors could either be fixed or it could be just constrained. So it could be either like fixed by giving exactly the itinerary, or one could only give the initial position and the destination and let the test purpose. So let's say, for instance, if I have my mobile car that will start here, and I would like it to arrive here, and I have my autonomous vehicle that should go straight, and I am specifying as a test purpose a collision.
I see.
We will generate all the possible trajectories that would lead a collision, taking into account that the car is supposed to only be straight and that the obstacle should arrive in the end here.
Oh, I see.
We can also,
Okay.
yeah.
Right. So the next question, Ziggy.
Hi. Well, so I was just interested. So, about that you analyze these MVC AI components, or the other type of those type of components based on changes and transformation occurred that humans be able to recognize. I'm just wondering if is there a method of retraining, relearning these components based on the kind of problems that you find, or based on, say, if they don't fill these specifications, based on, and then is there a method then reevaluating that and changing, say, either training data or something else, or some other method of generating them? Yeah, I was just curious about that. Yeah.
It's a very good question. Yeah, it's something that we are working on actually. So the idea, sorry, I just come back to the evaluation. Yeah, it's here. Yes. So the current data sets that contains these visual changes that are realistic are Cypher10C, ImageNet-C, and I think there is also some for detections. The problem is that they are not, like, their distribution is not fair. So I think as the first step, simply generating data sets that include the range of changes that is not affecting humans, and using it to retrain could enable to improve the perception component to handle this range. And this is a simple next step to do, because so far nobody established the range of changes that the perception component should be available, or now that is established. The first step should be, yes, to retrain the current perception components to be available to this range of changes. But yeah.
I see. Thanks.
Thank you.
Right. So next question from Sinem. Sinem, you have your hand up, or would you like to ask a question?
Yeah. Do you hear me?
Yes, we can. Yes, we can hear you.
So my question is about the second part of the work. So I was going to ask, how is the robustness related to your approach? Or so I mean, what is the definition of robustness in this context? That if we can say if it's reliable, it will be robust eventually. And the second question is that, is there any criteria of the users that you were collecting the human perception?
So for the robustness, so what we were arguing is that, so I think in the computer vision community, they will consider this work as a robustness. But what we are arguing is that according to the definition of reliability and robustness in the software engineering community, these are changes that are happening in the realistic environments, which is the definition of reliability, right? That your system should remain reliable under the changes that occur in the deployed environments. But I think the same work, if you would like to publish it in the computer vision area, we will have to call this robustness because so far this is called robustness. Like Cypher10C is called a robustness benchmark. So it's more, yeah, it just depends on how do we see it, yeah. But it's exactly the same. And then the second question, sorry, I forgot what was. I remember it was about the human experiments. So for this work, in particular, we simply defined two classes. It was either it's a car or it's not a car. And this was a binary classification on the question that we asked to the participant, was car or not a car. Then for second work, we did a bit bigger because the thing is that humans are not like machines. So machines will be very good, for instance, at telling this is a Bengal cat or this is a ragdoll cat. But humans, the question that we should ask them should be, is it a cat, a dog? Or so there is a different level of hierarchy for classification. So I guess for safety, we should choose one of them. It doesn't really matter if it's a Bengal cat or a ragdoll cat when we are on the road. It's maybe even doesn't matter if it's a cat or a dog. But it might be important to know if it's an animal or a human if there is no choice. So I guess these are some questions that should be studied to decide what are the hierarchy that is important to consider, and then to collect human performance given levels under this hierarchy to obtain the range of changes that is not affecting humans for solving this particular task. But the human performance depends on the questions that we ask. So in this case, these human performance are simply a binary classification.
Okay, thank you.
So I think we have just time for maybe one last quick question from Janina.
Oh, thank you, Rado. So Lina, also very nice work again, the second part, and it's very insightful. I think the way that you guys looked at this problem, which is definitely very crucial when you talk about autonomous vehicles, right? But what I'm considering here is you have a fixed image, right? So when you drive in a car, so either you in the car moves or the object at stake it moves, right? So have you considered, I'm not sure in the paper they consider like a moving image, but then your perspective of identifying correctly the object will be probably, I don't know, possibly hampered by these dynamic perspective that you have of the object. So including these, let's say, snapshots, different snapshots at stake of this figure. So like taking another dimension of how you see or perceive the correctness of the figure. Have you considered this?
Yeah, thank you very much. It's a very good question. And yes, actually, this is on what we are working now. So the idea of connected to the scenario would be this, is that if we have a scenario, it's a sequence of images, right? And then according to a number of frame, we should establish correctness according to this number of frame. Like if the perception component is not able to detect in the first frame, but given the 10 frames of images, 8 of the 10 are correct, it should be considered as correct. And this is the current step that we are actually just studying. We don't have yet something. We are thinking about what does it mean to be reliable given a sequence of images. And this is why we are interested into connecting this work to the simulator to see how is it. But it's a very good comment, yes.
Thank you. Thank you. Good luck with that.
Thank you so much.
So I think I will stop the discussion session here. I see there are further questions, including in the chat, but please email Lina with these questions. And I just want to say thank you again, Lina, for the very nice and thought-provoking presentation and answering these questions. And I would like to thank the audience for participating in the discussion, and I'm looking forward to seeing you again in 2 weeks' time at our next seminar. Thank you, everyone.